So I thought I should work out one of these examples for principal stress in 3D for you. So here's problem 2.12c, so this is on your homework, so I'll do one of them for you. So the stresses are given in the table, and I've put them into the stress tensor here. And the first thing you have to do is calculate the three invariants. So invariant 1 is just the sum of the diagonal, so it's minus 10, minus 5, plus 10, and so that equals minus 5. Invariant 2 is the determinant of all the combinations of x and y, so sigma xx, sigma y, tau xy, etc. So let me fill this in. So sigma xx is minus 10, 2, 2, minus 5, that determinant, plus the determinant of sigma x and z, so it's minus 10, 10, and then 3 and 3, and this combination is y and z, so minus 5, 10, 4, and 4. And so the determinant in 2D is just the downward diagonal minus the upward diagonal, so that's 50 minus 4 plus minus 100 minus 9 plus minus 50 minus 16. And so if you add that all up, you get negative 129. So the third invariant is just the determinant of the entire stress tensor. And so if you remember how to get the determinant, oh, excuse me. So if you remember how to get the determinant, you just pick a row, and then you do the submatrices. So it's minus 10 times the determinant of this minus 2 times the determinant of what's left over when you cross out the row and column of 2, and then plus 3 times the determinant of this. Okay, and so remember, for a 2 by 2, the determinant is downward diagonal minus the upper diagonal. And here we go. And so when you add that all up, you get 713. And so now let's summarize what we have. We have I1 is minus 5, I2 equals minus 129, and I3 equals 713. And so the eigenvalue equation was going to be sigma cubed plus I1 sigma squared plus I2 sigma plus I3 equals 0. And that should have been sigma cubed, not sigma 3. And so if you plug it in, it's sigma cubed minus 5 sigma squared minus 129 sigma plus 713 equals 0. So in the previous problems, I3 has conveniently been 0, and so it's been pretty easy to solve this cubic equation. But now, this equation right here is not the easiest thing to solve. I'm going to just plug it into my calculator and press the solve button. I'll be back in a little bit. So after struggling this for a little bit, I realized that I remembered this incorrectly. The actual equation is actually sigma cubed minus I1 sigma squared plus I2 sigma minus I3 equals 0. So I really hope I got that right in the notes, but if not, I'm going to mention that in class tomorrow as well. So the actual equation should be this. Okay? So we're trying to solve sigma cubed plus 5 sigma squared minus 129 sigma 129 sigma minus 713 equals 0. So now I'm going to plug this equation into my solver and see what we get. So it took me some time, but after going to Wolfram Alpha and playing around, I got these three roots to that cubic equation. So these are the three principal stresses, and typically you order them from greatest to least, including the signs. So this would be sigma 1, sigma 2, and sigma 3. Each of these principal stresses, or eigenvalues, is associated with a plane or an eigenvector. And the way to determine the eigenvectors from the eigenvalue is to put it back into the original eigenproblem. So if you remember, the original problem was the stress tensor minus I times the principal stresses when multiplied by the normal vector. So I meaning principal stress 1 corresponds to eigenvector 1, principal stress 2, eigenvector 2, etc. When you do that, that would all equal to 0. And so the way we did that was by making the determinant of the stress minus I times sigma equal to 0, the determinant equal to 0. So let's write out the stress tensor. It was minus 10, 2, 3, symmetric, minus 5, 4, symmetric, and 10. So what we need to do is to subtract the principal stress. So let's do the first one, 11.537, and you subtract it down the diagonal. So that, when multiplied by the unit vector L, M, N, and to let us know that we're doing this for principal stress 1, add the subscript 1, that will all equal to 0. Okay, so I'm going to do the subtraction first. So 10 minus 11.537 is minus 21.537. This is minus 16.537, and that's minus 1.537. Okay, so we need to solve for L, M, and N to make this true. Well, this is not a problem where you invert the matrix. First of all, the right-hand side is 0, and second of all, you can't invert this matrix. We made the determinant equal to 0. So let's just write this out longhand and go from there. So minus 21.537 L1 plus 2M1 plus 3N1 equals 0. To L1 minus 16.537 M1 plus 4N1 equals 0. 3L1 plus 4M1 minus 1.537 N1 equals 0. So the way to solve this is to solve one of the equations for one of the variables and then substitute that into the second equation. Here are three equations. So I'm just going to arbitrarily solve the first equation for L1. So let me go ahead and do that. So solving the first equation for L1, we have L1 equals minus 2 over 21 minus 21.537 minus 3 over minus 21.537. That was M1 and N1. So simplifying that, or dividing that out, we get L1 equals M1 divided by 10.769 plus N1 divided by 7.179. So what I'm going to do now is take this, remember this came from equation 1, I'm going to put that into equation 2. So we have 2 times M1 over 10.769 plus N1 or over 7.179. I missed the 9 there. Okay. Minus 16.537 M1 plus 4N1 equals 0. Okay, I'm going to simplify that a bit and come back. So doing all the math ends up in minus 16.351 M1 plus 4.279 N1 equals 0. So now you would think we've used that comes from equation 1 going into equation 2. You would then think, oh, we'll take this and put it into equation 3, but that will end up in 0 equals 0 because these are ill-conditioned equations. So what we do is then just solve this for, let's say, N1. Okay, so we're going to get N1 equals 16.351 M1 over 4.279, or if you divide that out, (3.822) M1. Okay, so solving this will not give you a unique answer. You'll just get ratios. So what I do is I set one of the L, M, and N's equal to 1, and then I solve for the other two. So in this case, let's start with M1 equals 1. That means that N1 equals 3.822, and then remembering, put that in for the L1 equation, and then L1 will equal M1 over 10.769 plus N1 over 7.179. That was equation star 1. So that will be 1 over 10.769 plus 3.822 all over 7.179. And if you do that, that comes out to 0.625. And so our eigenvector L1, M1, and N1 is, let's see, we said M1 is 1, 3.822, and 0.625. Well, that's fine. That's the direction that this principal stress is acting in. But typically, we want to make a unit vector. So we want to get the length, L squared plus M squared plus N squared. Okay? So let me do that real quick. And so that length came out to be exactly 4. So to get a unit vector, divide by the length. So we'll do this. And we get 0.1563, a quarter, and 0.9555. And so to summarize, for the first principal stress, which is 11.537, the corresponding unit vector is 0.1563, 0.25, 0.9555. Now, another unit vector that is also in this direction is the negative of that, right? Because when you square, negatives and positives don't matter. So either of these answers would be fine. And if you're using a computer program, when it comes to the eigenvectors, you might get either of these come out, or you might even get the one come out with one of, like, M1 is 1 or something like that. It just varies from software to software, as there's no real answer for the direction. But traditionally, and in this class, we'll make it a unit vector. So the magnitude squared, squared, squared has to add up to 1. Okay. You can do the same thing for the second stress and the third stress, but I'll leave that to you.